perfect repetition in a physical system is a liability. When structural patterns or temporal frequencies loop identically, they become highly susceptible to destructive resonance, where vibrations amplify until a material shatters, or operational deadlock, where a computational system repeats the same output continuously. To maintain structural integrity and process continuous new information, nature utilizes aperiodicity. An aperiodic system is highly organized, yet its internal patterns never exactly repeat themselves. It achieves infinite scale without ever falling into a predictable loop. This principle bridges the fluid dynamics of a biological network and the rigid geometry of a crystal lattice. The universal mathematical scaling protocol that enables this non-repeating growth is the golden ratio, represented by the Greek letter phi, or approximately 1.618. We can observe phi acting as a strict regulatory mechanism in two completely different physical domains. First, across the two-dimensional spatial planes of discrete geometry, and second, within the temporal processing networks of living biomaterials. Tracing this mathematical constant across both domains reveals exactly how biological neural networks can process infinite amounts of sensory data without suffering from predictable, repetitive errors. In discrete geometry, the benchmark for aperiodicity is the Penrose P2 tiling system, commonly known as the kite and dart. A regular pentagon yields acute and obtuse Robinson triangles. Combining these produces a kite and a dart. By definition, the ratio of their long sides to short sides and their surface area is exactly phi to 1. The matching rules governing how these specific shapes connect to one another create a unique structural condition. They allow for local five-fold rotational symmetry, but strictly prohibit any translational symmetry. You cannot slide a section over to match another perfectly. Because of this, these shapes can tile a plane infinitely. The structure expands forever without ever establishing a predictable repeating matrix. This aperiodic growth is driven by substitution rules, specific processes of inflation and deflation that dictate how these tiles hierarchically subdivide to generate larger structures. Through deflation, kites and darts decompose into smaller shapes, rapidly multiplying. A graph tracking the generated population at each step maps perfectly to the integers of the Fibonacci sequence. Because the population follows the Fibonacci sequence, the ratio of total kites to total darts in any sufficiently large Penrose pattern absolutely converges on the constant phi. In this spatial system, the golden ratio is an active algorithmic blueprint. It dictates the generation of infinite non-repeating geometric complexity from a simple set of starting shapes. The mechanics of spatial geometry map directly onto the temporal processing of biological systems, specifically within brain microtubules. Proteins solve this exact same physics problem. They continuously receive, process, and transmit sensory signals. A closed, repetitive loop stalls the biological computer. This data plot records the resonance frequencies of a single brain microtubule. The frequency values remain static over time, but the associated phase values shift continuously. Tracking these shifts reveals a nested architecture, 72 distinct processing clocks organized into a strict hierarchy of triplet bands. Unlike the acoustic resonance of a musical instrument, which scales in simple integer multiples, these biological frequencies are enharmonic. The ratio between these nested magnetic resonance frequencies scales exactly by 1.61, the golden ratio. The exact mathematical proportion that prevents a two-dimensional spatial crystal from entering a repetitive gridlock is actively utilized by biological proteins. They use phi to organize their temporal firing sequences into a continuous, non-repeating structure known as a time crystal. This introduces a complex biomechanical problem. Microtubules merge physical forces into one computational decision without utilizing a traditional wired electrical circuit. Empirical measurements show that there are three distinct resonance types operating simultaneously within the microtubule: mechanical, magnetic, and electromagnetic. Experimental data reveals a governing quadratic relationship that links these three physical forces: E squared plus phi squared equals pi squared. We can map this integration on a three-dimensional axis. The first wave represents mechanical base resonance, scaling at E. The second wave represents magnetic resonance, scaling at phi. The third represents the electromagnetic boundary, scaling at pi. Intersecting, they produce a perfectly synchronized output pulse. By adhering strictly to this equation, biomaterials integrate mechanical, magnetic, and electromagnetic forces to deliver a regularized, clocking mechanical change to their own physical structure. Biological computing operates as a highly advanced time crystal. It leverages these fundamental mathematical constants to lock disparate physical forces together into a unified computational beat. Tracking the integration of these forces requires new scientific frameworks, fractal information theory, and geometric musical language. Under fractal information theory, biological information is not stored as binary bits of ones and zeros. Instead, data is stored as specific geometric shapes mapped across a continuously clocking topology of phase. Looking at this triangular plot of the integer n, we can see how biological phases and ordered factors form a quantized linear metric. As the integer n increases towards infinity, the metric produces convergent ripples, generating distinct, self-similar fractal patterns in the data structure. In this framework, a geometric phase structure acts as a fractal seed. It is a highly compressed geometric shape. When stimulated by an incoming sensory signal, the shape unfolds, evolving to uniquely reconstruct an entire network of missing data. The golden ratio is the invariant metric linking two vastly different systems. It is the rule for spatial symmetry breaking in discrete Penrose geometry, and it is the exact mechanism for temporal synchronization in biological microtubules. Intelligence in this model is a fundamental topological property of nature. Living systems process information by using the constant phi to scale geometry infinitely, continuously computing without ever collapsing into a repetitive loop.